So we are now on high mass stars. This is the second to last thing we'll talk about before we go into galaxies and cosmology. So there's a little loose end that now we know a lot about stars, and over the past 20 years or so, a huge amount of information about planets around other stars has been discovered. So we'll stop and devote an hour or so on Friday before the guest speakers to talking about exoplanets. And by the time I finish the lecture and you guys leave this class, the information will probably already be out of date. So it's pretty new and exciting. So today we'll do high mass stars, black holes, curved spacetime. Friday, exercise 7's due, but I'm sure that people have questions in class, so please look at it. And then there will be a quiz on lectures 19, 20, 21. The practice quiz is already up on that. So that's star ages, the evil magnitude scale, and low mass stars. So no high mass stars, no general relativity, no black holes, just star ages, CMDs, and magnitude scale. And then we'll break a little bit early, go downstairs for the guest speakers. Okay, so we did half of this on middle of last week, so Wednesday. And the beginning of Friday is we want to fill in the rest of the HR diagram. And we did it for so-called low mass stars, which is in some sense a bit of a misnomer. These would be stars in between 2 and half of a solar mass. It's kind of hard to talk about the death of these stars, M stars, and brown dwarfs, because the brown dwarfs never really fused in the first place, so they're really just kind of super Jupiters. And even the M stars that do have a bit of fusion going on, they're going to live for longer than the age of the universe. So we can't really, we can talk about theoretically what would happen to them when they burn out, but who knows. So now we're going to go back and talk about the high mass stars. And a lot of the story is the same, but you just shrink the relevant timescales. So an O star, up at the top of this, maybe 30, 40 times the mass of the sun. It lives for a much shorter period of time, maybe only 20 million years. And the main sequence lifetimes are shorter, and everything is shorter. So we'll kind of say, hit the repeat button about cold cloud of gas, condenses into a protostar, spins out to a flat disk. There's a jet. Now we know there's a jet. And then it lands on the main sequence and starts merrily burning hydrogen into helium. For a star like the sun, that takes about 10 million years or so, the whole collapsing and spinning out and jet making and clearing out process. For a high mass star, this might be on the order of tens of thousands of years. All the same stuff happens, just fast forward. Okay. So just remember that this happens in groups. So what we went through on Wednesday was have a big cloud of gas like this. Maybe this is about 10 light years across. And what you're really seeing is a snapshot in time of actually, as far as the universe is concerned, a fairly violent set of events. So all of these regions where you see stars are going to set off jets and blow out a solar wind and then precipitate the collapse of the other stars around them. So you are seeing something that's actually fairly violent. You can think about it like this. And then we know that the initial mass function, the individual statistics of how those stars form, is really just the statistics. The picture is more than just a metaphor. It's really the statistics of breaking glass. So you get very few large stars, which are the ones we're going to talk about today, and then more and more and more kind of power law, more smaller stars. And at the end of the day, you get maybe for every O star you see, big bright blue O star, maybe there are 150 M's, and then even more stuff out there, because this is a limit on fusion and what stars you can see with visible light. It's not a limit on the shred of gas that you can potentially make. So you have the initial mass function, and we have our updated picture of star forming and star collapse. So it happens in groups, so we get clusters, and then we have a jet, which is really important. And anytime we get a really hot spinning thing, there should be in the back of your mind, I wonder if there's a jet. Or anytime you see something crazy and energetic in the cosmos, you should reverse that logic and say, hey, maybe there's a fast spinning energetic thing. Okay, so we're here, repeat the story, just do it faster. Now we're making high mass stars. Maybe a high mass star from cold cloud to main sequence takes 30,000 years or something like that, 30,000, 100,000, much less time. The one important difference, which will come back and be important later, is that you stopped and discussed whether or not the high mass stars or the low mass stars have puffy cores, and it, comparatively, they're all very, very dense by human standards. And it turns out that the puffy cores are contained within O's and B's, so really high mass stars. This thing has maybe 40 or 50 times the mass of the sun, but it's emitting 1,000,000 times more power. So that power and luminosity and therefore radiation pressure actually wins, and it puffs out the core of the star. So you actually expect to see, nobody's gone inside and seen it, but this is computer modeling and theory tells you that there should be weather and convective regions in the inside of the high mass stars, and no convective regions, very dense, kind of solid cores in the center of the low mass stars. In fact, low mass stars have very large convective zones, very small radiation zones, and they actually people have seen this. They have much nastier weather, pound for pound. So there are so-called M stars that emit these giant flares of material, which make our CMDs, our solar flares and stuff like that, look very wimpy by comparison. And point to make about this is at some point, you've got convective core behavior, and then you've got solid core behavior. At some point in the middle, there's kind of a switch over, and those will make these things called variable stars, which will be the heroes of distance ladder astronomy later on in the course. So I just want to remind you guys of that. Okay, so we have this. Any questions about the HR diagram while it's sitting here? You guys know how to read it, prepared for the final when you're asked more questions. Good. Okay. Mm-hmm. Yep. So the exam was graded with like a lot of latitude, and what I didn't want to see is numbers that don't describe stars, so that would be bad, and numbers that quite obviously describe like M stars or O stars. So, there's 3,000 there, and if you're quoting numbers like 2,500 or something, it's like, K's should be hotter than O's. So honestly, anything in between like 5 and 3, I was pretty happy with. So it was very approximate. But as long as you knew that the K's were somewhere to the left of O's, and the sun is a G star, you would have gotten it. So really you should have had it in between knowing sun's a G and M stars are there. You should have it bracketed to within that. And it was pretty, there was pretty wide latitude. As long as you were in the right spot, part of the HR diagram was okay. Okay. So now we're going to start asking the same questions that we asked about low mass stars for high mass stars. You get to the main sequence. The story is basically the same but faster. Cloud, jet, gravitational collapse. Now what happens when you're done with your hydrogen to helium burning in the core? And for a couple of reasons that we'll talk about, I'll be showing you a lot of slides that look like the low mass star slides. Namely, this is a nice kind of orange sun-like star. In your head, paint it blue, but it's like the same thing. So the story is the same, physically, is the radiation pressure is trying to puff out the star. In this case, think about it like an O or a B. The gravitational attractive force is trying to crush the star. That's why it's fusing. And then hydrogen runs out in the core, so it stops fusing. What's going to happen to my star? Somewhat surprisingly and counterintuitively. So the radiation pressure from fusion, if fusion cuts off, you would think that the halting fusion would halt the radiation pressure and the thing would collapse. And that's half true. So it's definitely true for the core. So the core stops fusing, radiation pressure stops puffing out the core starts collapsing. But then, kind of counterintuitively, you win by losing in a sense, is as the core of the star starts collapsing, what do you end up doing? You end up releasing a lot of radiation pressure through gravitational contraction. And it turns out second per second, gravitational contraction actually provides more energy than fusion. So just like a low mass star, high mass star will start puffing up. And so you zip off the main sequence, and you report to not the giant branch. There will be a different giant branch, but just take this line and move it over. I'll show you in a second why I don't have a really good line that describes the evolution of high mass stars when they leave the high mass part of the main sequence. But the story is exactly the same. Just move the line and paint the star blue. Okay. So radiation pressure stops, gravitational contraction takes over, and the thing puffs out. And what you get is an inert core of helium. It gets crushed. So you go from hydrogen-burning core, fills up with helium, turns off. The core itself contracts. The rest of the star blows up. And then at some point, the gravitational contraction is able to reignite a shell of hydrogen. So same thing that happened in just red giant stars. The rest of the star puffs out, so the solar wind increases, just like we had for low mass stars. Eventually, the inert helium core gets compressed and starts burning, in this case, helium to carbon, just like a low mass star. And you'll start getting double shell fusion. So you get an internal central shell of helium fusing into carbon in the core, and then a shell outside of it of helium burning. So same exact story up to this point. And this totally agrees with observations for low mass stars. Why am I not showing you an equivalent diagram for high mass stars with this statistically significant, 50, hundreds of low mass stars snaking their way from main sequence to red giant branch? Why can I not do that? And what am I relying on when I tell you this story? The M67 and the NGC are two different clusters. Yeah.
Are they
one's a little bit.
kind of star?
So this is actually this is showing something that somebody asked about, so I threw the slide in, and now I'm glossing over it. Actually, is that if you have more or less metallicity, you can actually shift where you leave the main sequence. So there is a little compositional effect, but roughly speaking, you can one or another. But yeah, these are two different clusters, and in fact, one of the clusters has different metallicity than the other one. So it does actually change the way that they evolve, in a sense. But yeah. Sneaky, there are two clusters on that. No, not significantly, but enough for people to notice. So these are all like, maybe one solar mass-ish, maybe a little bit less at this point. Why can I not show you an equivalent diagram that shows 50 to 100 O stars snaking off to the supergiant branch? And, have some very definitive things to show you. And yeah, in fact, the other issue is for every G star I have, like these things, which I'm showing you as they leave the main sequence, how many O stars would I have had back in a younger version of this cluster? Maybe half? I don't know. So just because of the paucity of the higher mass stars is that you don't get beautiful pictures like this when you're making high mass star CMDs. So part of the cheapness of recycling the slides is that you don't have the statistics to draw these beautiful lines and say, well, this is really weird, and what happens is this is the amount of time it takes to reshuffle the core, and then it's in the subgiant phase. So there's no really detailed information about how these things die. There are fewer of them, and they last much less time. So, same thing happens. It's just harder to get a lot of information about it. So at the end of a low mass star's life, you got something like this, a planetary nebula, where the solar wind has puffed the thing out, and it's left behind a remnant at the center. So we're basically repeating everything up until that point. And for a low mass star, we stopped at carbon. So something about the mass of the sun. And that's actually the fate of our sun, too, in about 4 billion years. So now I have 50 times more mass. Do you think I can get past carbon? So 50 times more mass, and therefore, much more gravity pressing down on the core of the star. So yeah, in fact, can I keep going all the way until iron? Probably. So for a high mass star, where the low mass star stopped at carbon, the high mass star will continue. And in fact, a high mass star on its version of the giant branch, the supergiant branch, that upper lobe, what happens is first it fuses a shell of helium and then central core of carbon and shell of helium. Then it burns through all of its carbon. Then it starts burning carbon to oxygen and nitrogen, and actually kind of interesting and complicated ways burns through the oxygen, makes it to neon to magnesium, and then all the way up to iron. So you can get all the way up to iron. And the same thing happens, except you reshuffle the core, you ignite the next stage of fusion, you reshuffle the core. When that burns out, you ignite the next stage of fusion. So hidden in the center of a supergiant is this, you kind of think about it as like an onion where there's layer after layer after layer of multiply fusing shells until you finally get into the inert iron core. And you cannot get past iron because iron has the lowest mass per nucleon. So if I convince a proton to go from hydrogen to helium and helium to carbon, less mass, therefore power is released, this stops at iron. So if I were to make something bigger than iron, I would have to put in energy to pay the E equals mc squared cost to make mass. Or if I stopped before iron, I could actually compress that into larger nucleus with less mass per proton and get energy out. But iron's where it stops. So that's the lowest mass per nucleon. Okay. So I end up here. And now, after some amount of time, I basically have a bunch of shells of different things fusing, and there's a giant cannonball sitting in the center of the star. And feel free to ask how on earth people, know this. And this is very, very differentiated, but we can't go any farther. In fact, this is the beginning of the interesting part of the story, but I'll just point this out, is that honestly, like most physics, at the heart of it is easy. It's just, either the verbiage and the way that it's described is kind of annoying, or you just don't really want to do physics in the first place, so you tell yourself it's hard. The two exceptions to that are nuclear physics and fluid dynamics. Unfortunately, both happen in stars. And this is some of the stuff that people have pieced together about what's going on in the core of a high-mass star. So this is the so-called CNO cycle, and it almost looks like one of these biological catalyst reactions where essentially what's happening is the carbon is almost acting like an enzyme, and it's helping the nitrogen and oxygen be made. And then there are more interesting, these little kind of ladder pathways where carbon and oxygen get together and they jump immediately to silicon, or you can go through two oxygens, and it gets like very, very complicated very quickly, and people spend their entire careers working on stuff like this. And this is basically what goes on in the simplified schematic way inside of the core of a high-mass star. So you start with a whole ton of protons, and then you start following this through, and then eventually we'll get to this. So this is, so we get up to iron, and then more stuff will happen here, and we'll figure out how to make gold and uranium. Yeah? So the CNO cycle is basically, if you look at step 1, you start with a carbon, and then you end with a carbon. So the carbon basically gets used as an intermediary to make helium. So the analogy to biology is if you know how an enzyme works, is that it's this big molecule and it grabs two other smaller molecules and helps them combine. So essentially the carbon in the CNO cycle is going from carbon all the way up to nitrogen to oxygen, then back to carbon, and helping hydrogens combine into a helium. So it's almost like the carbon is acting like an enzyme to help things. And it speeds up the process of making helium. In the sense that it's never been done in a laboratory, it is a theory. But I don't think anybody is actively disputing the CNO cycle. So I think the issue is that once you make carbon in stars, and you see it here, is that things start happening really, really, really fast, which we'll talk about in a second. So people are like, what's going on? And then somebody came up with this idea of the CNO cycle. But the real point of these slides is that really sort of incredibly complex stuff is happening, and things get much more interesting than just protons bashing into protons, in fact. So, yeah, this is the part, and honestly, this is probably true about 2 weeks ago, is that when you say no, you should kind of like qualify. People believe that something like the CNO cycle is happening inside stars because it's the best theory about how so much helium gets made, and the helium is going to be the thing. It's not on here, but, oh, yeah, it is. So there's a thing called the helium ladder, or the alpha ladder, where just helium, 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 and you race from oxygen up to magnesium, and it requires a whole bunch of helium. People, back in 1975 or something like that were wondering, where's all this helium coming from? And so somebody said, well, you could do this, and the energy says that you can do this thing where you start with carbon, and then you cycle through carbon, and you spit off this helium, and it's just basically makes a ton of helium inside the star. And so no means nobody has a better theory about how a star works, aside from the fact that there's a ton of helium that lets you race up to iron and magnesium through this alpha ladder, and the CNO cycle is how you get all the helium. So, yeah, no, quote unquote. Best working theory to describe how the stuff is happening, basically. Questions? Okay, so that is a joke, but I'm going to remove this for the online slides just to mess with everybody. Okay, so while we're doing this is basically the details of what's going on in this chunk of the HR diagram. So live a short, hot life on the main sequence, and then you start burning into higher and higher elements. This is all happening in the supergiant branch. It's hard to, again, get statistics on this and show you a beautiful picture of the evolution like we saw for the red giants, where you saw this thing subgiant up and then helium flash and horizontal branch out. You can't really do that for the supergiants, again, because this happens so fast and there are so many fewer of them, relatively speaking. So if you see some stuff in the supergiant branch, basically you really have no idea what's specifically going on inside their cores. You don't know if they're on carbon. You don't know if they're on silicon. You hope they're not on silicon, at least when you're seeing them, for a reason that we'll get to in a second. Like, basically, there's just this, very fast, we're talking about tens of thousands of years or hundreds of thousands of years fast evolution all happening in the supergiant branch, where they may be fusing anything up to, nickel and iron, up to nickel and iron. Okay. So there's a law of diminishing returns, and then you also get this neat effect where things like the CNO cycle. The analogy I would give you is like the first omelet that you make if you work in, a kitchen. It takes a really long time because you got to chop all the onions, and then you got to heat up the pan, and then slice the butter, and basically do all the prep work. And that's why a lot of the main sequence stuff takes a long time. The second and third and fourth omelet you make of the day actually takes less time because you already have some stuff made. Like, you already have some deuterium and you already have some helium. So things start going faster for multiple reasons. And this reaches its absurd conclusion in silicon to iron. So the silicon shell that's actually making the iron, as far as people know, again, quote unquote know, lots of theory and guessing, is that the silicon shell burns for like 5 days. So think about, that's not like something that really, blows your hair back from a normal human perspective. But think about all of the other timescales of cosmic evolution we've talked about so far. So it takes 10 billion years to kill a star like our sun. It takes, this thing took it 10 million years, which is actually a very short time, relatively speaking, to burn through its material at the core, its hydrogen. And now we're talking about 5 days. So things really pick up fast. And again, that's why we don't have a lot of detailed information about this. It's a lot of supposition. Okay. So we're here, and let's say that we're at the end of that 5 days of silicon burning. So we have like the full differentiated giant cannonball at the center, inert iron core, and all this stuff is going on. We don't have anything to turn off because the iron core isn't fusing. So what happens now? So any guesses about what happens as I'm, piling iron onto this core? So we could just have this thing kind of die with a whimper, right? Maybe just everything turns into iron and there's a cannonball sitting in the cosmos and the other layers just kind of peter out and it sits there. That is really not what we see. And to understand what's going on, unfortunately, we have to talk a little bit about chemistry, in a sense, and atoms. And this picture that you have of solid matter is actually fairly wrong. And the reason to talk about it is because the thing that's keeping this star from being crushed is, like a normal human, why is this star not collapsing? It's got an iron core, but what does that really mean? So it means that iron is solid, okay? And usually you don't have to go through your life like re-examining why iron or solid material is solid. But once you start piling like 50 solar masses of material on something like this, you have to wonder what solid is, why solid is solid, and can solid remain solid under such great pressures. So this picture of an atom that you have, the electrons are like this cloud of bees, and then there's a nucleus at the center, and you get these cute little pictures on the cover of a chemistry textbook, is actually really, really, really wrong. And the relative sizes are actually more like, hate to do this to you guys, but if the nucleus was the size of a grapefruit, the electrons would be out in like past Bothell or something like that. So there's a lot of empty space inside of these. And people show you these pictures as diagrams. There's a lot of empty space inside of quote-unquote solid matter, right? So what you would call being solid, a chemist or a physicist would say, actually, this is electron degeneracy pressure, which is the fact that I can't put two electrons in the same spot. And so what's really making solid solid is the fact that through some quirk of nature, electrons stack like bricks. And this is the type of thing that's actually holding up a lot of things in the cosmos. You really, again, don't think about it too much. Is that what keeps the Earth from collapsing under its own weight? Well, it's the fact that the Earth is solid. But that's really electron degeneracy pressure. What's keeping the fruit basket on top of the table from falling through the center of the Earth? It's the fact that the table is solid. What that really is, again, electron degeneracy pressure, and there's a lot of empty space in there that you don't think about on most days. So you start thinking about it on something like this. And the reason a white dwarf star isn't collapsing isn't because it's a bunch of neutral atoms stacked up. It's actually, and this is why they're so dense and so comparatively small for their mass, this would be about the mass of the sun, is that this isn't neutral atoms. So this is literally just a stack of electrons. So very, very, very dense. And a lot of the empty space has been removed in this. So this so-called electron degeneracy pressure is the second to last line of defense against gravity. So this is what it really means for something to be solid. And I'm sure you've seen a picture like this at some point in your life, these terrible chemistry diagrams where you put two in the s orbital, one spin up, one spin down, and then you start filling stacks of 8. And this is a good schematic. You think about the electrons like bricks. You'd fail your chemistry exam if you put all of the electrons down in the lowest orbital. But remember that there's a lot of empty space in there. So, it's basically like a factor of a million in between the size of the nucleus, for instance, and the distance to the electron. So about 6 orders of magnitude. Okay. So this is what it means to be solid. Any questions about that? So the most important thing is like how much empty space is in the space. Good. Okay. Yeah, I mean, it's in some sense whether or not the size of an atom would change. Size of an atom does change. You kick an electron up to an excited state, it gets farther out on average, and then emits a photon, drops back down. But remember that that's a statement about normal neutral atoms, like a nucleus surrounded by the appropriate number of electrons, which is a situation that you have here and here. It's not a situation you have at the center of a star. So this stuff is so compressed and so hot that you don't have neutral atoms, so you don't get to play these games with, well, I make the thing a little bit bigger, so do I let the star breathe as it expands and contracts and absorbs more or less light? So, and literally exactly what you said. So those are the bands that you guys saw in the discharge lamps. So that's a game that you can play here, and you can ask questions about, well, I take some nitrogen in our atmosphere and I have it absorb some light. Does it get a little bit bigger? Do the clouds swell or something like that? It's very true, but that's just not it's not something that you have to worry about here because you don't even have neutral atoms. So, we've got nucleus and then stack of electrons on top of it, and just realize that these things that you think are, one, uncrushable, and two, have this picture in your mind of them being like relatively solid, this kind of beehive of electrons surrounding this, or cloud of bees of electrons surrounding this hive of a nucleus. It's pretty far off, and there is a lot of empty space there. So it turns out you can actually crush an atom, if it were neutral, or stated alternately, you can have an electron and a proton come together and suddenly occupy much less space than it did before. And you guys actually already know how that's possible because there was this alchemy that happened in the center of just, we're not even talking about exotic stars, just like a normal main sequence star in the so-called proton-proton chain. So if you remember, we just said get 4 protons and then gypsy magic happens, and then you get a helium nucleus. And a helium nucleus is 2 neutrons, 2 protons. So I started with 4 protons, and then suddenly I turned 2 of them into neutrons. How on earth does that work? So it turns out that works through this process where you have a positively charged proton, negatively charged electron, antineutrino, don't worry about that unless you want to, and the positive and the negative come together and disappear and make a neutron. So the way that you would think about this in terms of a neutral atom is, I have a hydrogen atom, which is composed of a proton and an electron, and it takes up a lot of space, and then I smush them together, and what I can do is I can convince the electron and the proton to suddenly transmogrify into a neutrally charged neutron. And this isn't, abstract, theoretical, whatever. This is required. This is what the sun is doing to thousands of tons of hydrogen every second in its core. So it's absolutely grabbing an electron and grabbing a proton and smashing them together in its very dense hot core and then turning them into a neutron. And
is that neutron the same?
Plus the mass, so the proton, the neutron, the proton and the electron, if you add their masses together, there's a little bit of a discrepancy. Neutrinos are basically massless. Their masses are teeny tiny. The discrepancy is the energy that is required to do that, or the energy that's liberated as it happens. Yeah. So if you add up, you can't add masses anymore like you do in momentum problems in physics 1. Is here you have to add up relativistic appropriate things. So you have to add up mass and energy, because E equals mc squared. So you don't conserve mass, you conserve mass energy in processes like this. But absolutely, yeah. If you do the right accounting, you've got to conserve mass energy. And it puts a constraint on, things like the neutrino mass. Yeah. So this is happening, and this is happening a lot. And, we didn't really talk about it because it's not all happening at once in our sun. But, it is taking some electrons and protons and turning them into neutrons and then putting them to good use. So this happens in the core of a supermassive, so a very high mass star, if you can get the critical pressure. So now we're talking about taking entire nuclei, which are comprised of a bunch of protons, and then there's the sea of electrons floating around. And if you squeeze hard enough, you get this all to happen at once. So the equivalent would be grab, some solid bit of material like this. And if you could squeeze it hard enough, you could have all of the electrons overlap with protons. Neutrino would fly by, set all the reaction off, and then all of a sudden, boom, you would turn what would otherwise be a very big empty space atom into basically the size of a neutron, which is much, much, much smaller. Okay. So kind of missing piece, but you've seen it before. You just need to squeeze this stuff really, really, really hard. But those are precisely the conditions we get. So this all happens at once if you get past a critical mass in a high mass star. So the end stages of fusion, you're burning all the stuff, you're making a lot of iron. The iron is not fusing, it's just sitting there inertly, and it's under an incredible amount of pressure. So all of a sudden, the iron gives way, and the protons and the electrons in the iron suddenly turn into neutrons. This happens basically all at once, and the core disappears. So, I'm not talking about astronomy like 1,000 years all at once. We're talking about real to us all at once, over the course of minutes, if not seconds. So the iron core, if you get to a high enough temperature, disappears. So imagine that you're, a thermonuclear ball of fusion, and you have, maybe 10 to the 31 kilograms of material, and then all of a sudden the center disappears. What's going to happen to all of the outer layers of this stuff, which is actually still fusing, so it's still a thermonuclear explosion. It's just, instead of taking place on the surface of a cannonball, the cannonball basically just magically vanishes. So what's going to happen to this star? Yeah, so the whole thing starts collapsing. And at the center, there's, much smaller fraction of material. What used to be, something about the size of planet Earth maybe is now the size of Seattle or even smaller. So this tiny ball of neutrons, so basically, a giant nucleus, is sitting there, and everything else starts rushing in. The stuff is powered by the fact that it's basically a giant thermonuclear explosion. So by the time it gets to the center of the star and starts interacting with the other material, it's going about the quarter of the speed of light. The temperature is, hundreds of billions of degrees. It doesn't even make sense to talk about temperature at that point. And there's nothing there to stop it aside from the other onrushing material. So this is what's called a core collapse. Yeah?
The iron core disappears.
Yeah, I'd say disappears. Yeah.
Would there be it wouldn't be like
it's a lot of empty space. So like what used to take up, so it shrinks by basically a factor of 1,000,000 in linear size, which would be a factor in 10 to the 18th in volume. So think about it as a ton of empty space, but then sitting at the center is this comparatively small box of neutrons. So if you imagine taking the entire, maybe like the mass of the sun and compressing it into about the size of like Green Lake or something like that, that's what you're talking about. So we will have a video of this. I actually have an even cheesier demo. So yeah. It's not to say the core is like an oven creating the temperature. The temperature comes from the fact that this stuff is starting to fall in. And as gravity pulls it in, it gains energy and heats up. And in fact, it was hot to begin with because this whole core is a thermonuclear explosion. So the collapse is kind of hard to model, but I'll show you guys the rebound. So as far as the collapse goes, just imagine you totally remove the iron here, and then everything just falls into the center. Right? So, like kick the pole out of a tent and watch it collapse kind of thing. Okay. Maybe. So these are our options. So you have this stuff falling in, right? It's falling at an incredible rate and really high temperature. But don't forget the neutrons, because they don't take up a lot of volume. However, they're the densest thing that you can envision in the cosmos. Basically, this is something about again, size of a couple of kilometers, reasonably big, size of downtown Seattle, basically. And it's all stacked neutrons. There is no empty space. So this is where you start, if you've ever heard this stuff in science documentaries, these like ridiculous statements, a teaspoon of neutron star will be more mass than Mount Everest and things like that. This is what they're talking about. It's basically an atomic nucleus, but it's the size of small town or something like that. So all of these valiant neutrons are sitting at the center. This used to be about a solar mass of iron and a sea of electrons, and they're all stacked at the bottom. And basically, this material, this quarter of the speed of light, onrushing, 100 billion degree stuff is coming right at them. So there are two options. So this is basically the same thing as electron degeneracy pressure. We have to stack them. They can't sit in the same quantum state, but they're neutrons, so you call it neutron degeneracy pressure. So this is, they're there because they're solid, and boy, are they solid. Again, you take a teaspoon of this stuff, and it weighs as much as like Mount Everest again or something like that. Do you think they're going to win? Do you think they're going to fend off this onrushing material of maybe like 30, 50 solar masses coming at them? And what would happen if they lost? So they get smushed all over the cosmos. If they win, this stuff just bounces back off, right? Yeah, you get an explosion. If they lose, they're backed into a corner, right? So what would happen? There's no more space for them to run into. Could they possibly lose? Yeah. It just like rips a hole in space-time. Okay, so we could vote. So how many people think the neutrons win and they fight off the infalling matter? How many people think they lose and they don't fight off the infalling matter? Okay, everybody who voted wins, because there are two options, and one results in a supernova, the other one results in a black hole. So this is a kind of cartoony, step-by-step picture of a core collapse supernova. So this is the neutrons valiantly fight off the onrushing material. And this is a pretty not to scale, so this is really close zoom in on the core of the star itself. So you got the super differentiated core, the iron core starts collapsing, basically shrinks to almost nothingness. All of this stuff rushes in. The core fends it off, it smacks into the core and rebounds, and then it explodes. And you can see these explosions. Basically, they shine, for a while, about as much energy as the entire galaxy in which they live. So they shine about, 100 billion stars worth for a small amount of time. Okay. Anybody think there's something kind of fishy about this? It's baffled people for a while, and it's got the goofiest explanation. Is that the first people to propose this theory were like, yeah, well, the neutron stars bounce off, and then things explode, and it just kind of makes sense. Makes you feel like, yeah, this is where these supernovas come from. Have you ever dropped a ball from some height and had it fly off, like mile up into the atmosphere? Have you ever gotten more energy out of dropping a ball than you put in? Should you suspend that intuition just because it's like a big, cool star? So we're really talking about, the speed itself is crazy, but we're talking about dropping material in, some gravitational well, and it bounces off. It bounces off a core of neutrons, but, whatever, they're just sitting there. And then it bounces back. You would think it would just end up at the same height it started with, right? So have you ever, which is to say, take a bouncy ball and you drop it. When I drop this, will it hit the ceiling? No. So this is a pretty unexciting, quote-unquote, explosion. And then people started kind of spewing this nonsense about how, there's like this extra blast of fusion and something else is going on, and there's this power liberated by it. And it turns out the answer for why core collapse supernova are so energetic and the explosion of the outer layers of gas are so powerful is kind of the explanation behind a either intro physics demo or like a kid's toy. So now I have a whole bunch of stacked balls, right? So yeah, and I'm going to drop this from a very small height. So this is basically what's going on in a supernova. Is the outermost layers, they're not bouncing off of a static ground. What they're doing is they're bouncing off of the layers that already bounced off the neutron star. And then the outer layers are bouncing off of those, and the outer layers are bouncing off of those. Oh, sorry, it's got a ring at the top. And so what ends up happening is they basically catapult the shell at the edge of the core collapse supernova with an incredible amount of energy that it didn't have before. So there's this kind of momentum transfer thing going on. And it took people a while to figure out exactly what was going on. But you can get more energy out than in just for the outer layer. But realize it came at the cost of some stuff sticking to the neutron star. Yeah? So the question is, why wouldn't the outer layers escape or fly off at the moment of collapse? So they're peeling off a little bit before the collapse, just because the star has puffed up into a supergiant, so it's bigger, even though it has the same mass. So just for the sake of this discussion, let's just call this like a 50 solar mass star. So I have a 50 solar mass star, and it goes from this big to this big. So what's going to happen to the gravity that's trying to keep this part of the outer layer on? Less, right? Because gravity goes like radius squared. So there will be a bigger solar wind already. But then, whatever, let's say that you do have enough gravitational force to keep you on the star, and then all of a sudden the core collapses, which doesn't mean that it disappears. It just means that the solar mass at the center has just gotten smaller. What happens instantaneously? What happens to the gravity that this thing feels? So if I were to compute it, what I would do is I would count up all the mass inside of its radius. Has the mass inside of its radius changed? No. Has the location of the center of the mass changed? No. So the moment this thing collapses from core to neutron star, a little bit of gas right here actually doesn't know the difference. The only time it starts noticing is when the inner layers have started sloughing off and falling in, and then all of a sudden it feels the inner layers of gas below it. And it's like, hey, where'd the floor go? So imagine that you're on the 10th floor of a building and somebody detonates it's actually pretty morbid, but whatever. So you just start feeling the floor go out from under you. There's no instantaneous change in gravity. And then because of the neutron star, then all of a sudden the floor rebounds off if the neutrons win and catapults you up into the outer layers, at least, just throws you up with an incredible amount of energy. As you guys saw from that, I'm not going to do it again because you kind of lose the ball, is that I dropped this from about like 5 centimeters height and it hit the ceiling. So it's actually a really good way of transferring lots of energy to the outer layers, and they just fly off, taking with them chemically enriched gas out of which people like us are made. So the mass, as far as people know, there could be some other things going on as the way that you collapse or something, but it's really the biggest predictor is the mass. So honestly, people should have cut just because it's not 100% clear where that dividing line goes, it just doesn't make it into textbooks, is that if you have like 50 solar masses, you're probably going to be a black hole. If you have 10 solar masses or 8, I think the cutoff, as far as people know, is like 8 or 6 or something like that. I think it's 8. So if you have like 6 solar masses, you're probably going to be a supernova.
Is there anything? We'll start like.
It's a very binary thing. So at the end of your life, so all of these things have above what's called the Chandrasekhar mass, which is the mass required to have the iron core collapse. So that's really the cutoff in between high mass and low mass, is that if you have enough to get to iron, and then if you have enough to get to iron, you have enough to kind of crush your iron core. But the divide in between the types of high mass stars is, do you have enough to rip the neutrons through a hole in the cosmos and make a black hole or not? And that seems to be about 8 solar masses or so. Don't quote me on that. Something. You mean like planets and things? So if the high mass star that's going supernova had some planets around it or whatever, odds are those planets, if they were close enough, were vaporized or eaten by gas drag or something when it went from main sequence to supergiant. So when you go from main sequence to supergiant, if you look back at this, and this one's got some radii on it, is you basically went from 5 solar masses to 100 solar masses. So imagine the sun increasing by a factor of 20 or so that gets it out to near our orbit. And the same thing will happen for supergiants. So they will probably, if not get scorched, they'll experience gas drag and fall into the center of the thing. If they didn't, when the thing goes supernova, they will absolutely be vaporized. So you don't really think about it too much, but if you turned your hairdryer on a blob of iron or something like that and you just left it on, eventually you could totally ablate the blob of iron. So a little planet would have no chance of surviving a supernova blast. Very easily they would just be... in fact, people found the first planets around other objects found were around neutron stars, and people were very skeptical and upset by that, because if you compute the energy that's released during this, it's enough energy to just completely vaporize a planet like Earth or Jupiter or something like that. So it would basically just be blown off. Okay. The energy that would be released during the supernova would just melt the whole thing and turn it into a gas of hot iron that is totally indistinguishable and mixed with the gas of hot iron that's going to be flying off of the neutron star. Flying off the supernova. Yeah, it seems crazy, but if you take a chemistry textbook and you look up the heat of, latent heat of fusion, latent heat of vaporization for, Earth, like iron, and you figure out how much energy it takes to completely vaporize a planet like Earth, this thing has more. A lot more, actually. Yeah, weirdly. So, yeah. Any other good questions? Okay. So option 2 is that the valence band of neutrons does not have enough neutron degeneracy pressure to resist the infalling matter. And that happens at higher masses. And this is a cartoon, and the answer is you rip a hole in space-time. So this is the best theory about how you make black holes, and we now believe that there are black holes. First direct observation of them instead of kind of indirect evidence, which we've had since the 70s. Direct observation of black holes happened in September of last year. So absolutely these things are real. It's not sci-fi. And the best way to make them is with a very high mass star. And you just let this stuff go in, and you just rip a hole in the fabric of space and time. So we'll talk about that after the break. Okay, so these are the best I can give you, if these are still up to date. I forgot to check. And the important part is to notice the time scales. So how on earth do people know this? And it's this really interesting kind of set of data which is bookended by people pouring through manuscripts from the Song Dynasty of imperial China, and very high-tech supercomputer simulations is where a lot of our story of supernova come from. And this fraction of a second and this explosion of the supernova itself, basically super high-tech, cutting-edge simulations. You see something that might look like this. And I'll turn the volume on because I think there's a British narrator, which is always nice. And even this is out of date because I think this video is a couple years old, but same idea. Is that nobody, you can't go into the core of a high mass star and drop a probe in there, certainly. So.
Here, slowed down millions of times, is what is experimented with.
experiment means calculation. But
the complex pattern of an exploding star shown in astonishing detail. The beautiful and precise motions that scatter the building blocks of life out into space.
That explosion of a star throws the elements that were formed in the star outwards. They go outwards into the galaxy, and some of them gather together, form other stars, solar systems, even planets like the Earth.
These images, captured by our most powerful telescope, show the remains.
so these are nicer pictures, but the idea is that people work really hard, and the second part of, second branch of physics that is truly difficult is fluid dynamics. And what this is a magnetically active and charged fluid. So it's magnetohydrodynamics, and it's turbulent, and there's fusion going on. This is basically, to write down the answer with pen and pencil, you should really give up. So for option one, we'll talk about option two after the break, the black hole, is that we can kind of dovetail back into the low mass story, and at the end of a low mass star's life, it left behind two things for us, which with the evidence that we used to create this whole crazy story in the first place. And for a low mass star, it was a planetary nebula. It was basically the solar wind of chemically enriched stuff, and at the center was a white dwarf. It was a big ball of carbon under a lot of intense pressure. And that basically, said, this checks out. I see a ball of carbon. You stopped at carbon. I see some chemically enriched cloud of gas. You blew off a lot through the solar wind. So the same is true for the core collapse supernova. Is you get, it's not called a planetary nebula on steroids, but it really should be, supernova remnant, giant cloud, much, much, much bigger than planetary nebula. And then there should be something at the center of that, and that's the ball of neutrons. Wouldn't be able to see that the way you'd be able to see a white dwarf star. So this is something that should contain basically every element that you can think of and some other ones. So this is SN 1006. The name means something. It's about 60 light years across at this point, so that's very big. It's maybe 20 times bigger across than the the cloud out of which our star condensed. And we know that it went off in 1006 AD because there were a whole bunch of records that people were able to go through. So there was, this is the Dark Ages in Europe, when if you saw a bright star in the sky that wasn't there yesterday, you would keep quiet about it lest they burn you at the stake. But not true in other parts of the world. So, you go through these historical records and there are guest stars. There are a couple of guest stars from 1590 or something, and then 1600 or so. These would be visible, pre-telescopes. These would be visible with bare eye. And these things would outshine the brightest planets, so you could see them during the daytime. Is what I presume that's what this says. I don't know. Could be instructions on how to make wonton, something. I don't know. This was visible for a month. So that's kind of, and it's weirdly universal, is that if you see a supernova, the really, of either type, core collapse or white dwarf, which we'll talk about later, is it's basically a month or so. So really wonderfully human calibrated timescales, the super bright part before it fades out of, visible light. Now, certainly if you have a telescope, you can see it. Obviously, this is a modern picture. But let that sink in for a second, is that within 1,000 years, this thing has gone from very small to 60 light years across. So that is a tremendous explosion. And it's not even really a thermonuclear bomb. It's like the cheesy physics demo thing that's powering this. So it's very efficient, really. Yeah. Other questions? Okay, so the other thing we had in star mass death was the white dwarf, so the remnant of the stuff that didn't burn. If you don't make a black hole and you do have a core collapse supernova, so the valiant band of neutrons wins, the valiant band of neutrons gets to remain and celebrate for a very long time. So you actually would expect, and at first you're like, why would you ever see these things? This is something about the mass of the sun. This is something about the size of Green Lake. So again, downtown Seattle. And if you remember the figure skater thing where you have a giant cloud of gas and then it condenses, pull your arms in, spin faster through the conservation of angular momentum, at some point this was a light year across cloud of gas. And that mass over the course of its protostar life to main sequence life to iron core life to neutron star life has condensed down to a couple of kilometers from about a light year. Do you think it's spinning fast? Yes. So it's spinning very, very, very fast, like thousands of times per second. Yeah. It could be. The problem is these things are so small that to directly measure the temperature that you would, in the same way that you would measure the temperature of a star, would be very difficult. So we see these things, but we see them because of the radiation they're emitting, because they're basically spinning very fast and they have a magnetic field. But yeah, I suspect they're really hot. I don't know. Problem is they're so small surface area, and the total luminosity goes like surface area that you don't look at them, say like high temperature. So I would presume so. But I don't know of any number or measurement. Okay. So you have this thing, it's very small, maybe big ones are about the size of a city, even smaller in some cases. They spin about 1,000 times per second. And they have tremendous magnetic fields, because it turns out that neutrons have magnetic fields. And so what you see are these blinking things in the cosmos. And before people really connected the dots, and they have this legacy of two names, is people will talk about pulsars and they'll talk about neutron stars, is that all pulsars are neutron stars. And if it's a neutron star that happens to be beaming and spinning so that we can see this beam of radiation as it goes past us, we call them a pulsar. So they're kind of like lighthouses in the sky. And this is, I think, a radio image. So this would be microwave or radio light coming by, and this thing is spinning really fast. So, every 33 thousandths of a second, this thing blinks. So, in fact, that's how you refer to this object. You'd say, like, hey, have you looked at the 33 millisecond pulsar lately? And somebody would say, like, why? So we see them, in fact. You don't see them in the telescope sense. You see this beam of radiation, radio microwave that they're sending out. And, if you find a cloud of gas that looks like this, for instance, maybe the first thing you do is point a radio telescope towards the center. In fact, hidden on this, so these artifacts that we sent into the cosmos in the Pioneer program, is that as well as instructions in a universal language based on the hydrogen wavelength, on how to make a record player and what humans look like, there's this. Any guesses about what this thing is? Yeah, the solar system is located right there. And if you were to tell aliens where our solar system was to come get us, I don't know why they did that. Nobody asked me. What do you think the best coordinates or landmarks to use would be? Because if you give us landmarks, I'm an alien and I find this random probe in the middle of nowhere in, 10 billion years or something like that, and you give me directions based on, like, for instance, O stars, is that a really good idea? And those O stars are not going to be around, right? And there are, even O stars, which are relatively rare, there are so few of them, right? So the best and most distinctive things that you can pick to give landmarks in the cosmos are pulsars. And what this is a whole bunch of locations of pulsars, and then etched in these lines are a description of what their frequency is. So this would say this pulsar with this frequency and this pulsar with that frequency. And presumably the aliens who find this, which will never happen, would find, take it and triangulate and find us. And I don't know, come take all our stuff. So again, terrible idea, but it's a nice thought. Okay. Is there any
On these discs, is there any
I don't.
like this hypothetical sees that
Yeah. In kind of an implicit way, there is. I don't know if they were thinking about it, but they're powered by radiometric batteries. So you have uranium, and the uranium decays, and uranium has a half-life of, like a couple of billion years. I forget offhand, but it's on the order of a billion years. And if the aliens were smart enough to realize that that's the power source and it was completely enriched uranium, they could look at the half-life and say this probe was launched however long ago. They didn't do, as far as I know, they didn't do anything clever by say this was launched when the black body radiation at the back of the ground of the universe was 2.73 degrees or something like that. So it would be a really hard thing to state. But the universe actually does have some, has like some time pieces kind of, etched into the background, in fact. So that's how we know the Big Bang was so long ago. So you could have had this universal time coordinate. I think it would have been hard to explain, though. But yeah, you could probably look at the batteries and say, yeah, I know. I mean, the record player, I think, is kind of a stretch, but whatever. I mean, this is like 30 years ago. It's not even like a cosmic time scale, and it's already kind of embarrassing that we're telling them to make a record player. But okay. So any questions about that stuff? Okay, so we have a loose end, and the loose end is that we managed to make everything up to iron, which is impressive. Know where every single element found on Earth up to iron came from, and you can tell its story. And next time somebody takes a piece of charcoal, you can just really think about how amazing the carbon in that charcoal is instead of just like a charcoal briquette. What about all this stuff? So we have, uranium and gold, things like that. That's all in there. Where does that come from? Any guesses about where the uranium and the gold and the silver and things like that come from? Well, what would you have to do to get past iron? Because hopefully you believe me, but we'll just say that the universe started with nothing but protons, and then it made some helium. So basically, the initial conditions of the universe were this. If I had some iron, or some lighter elements, what would I need to do to make uranium? Yeah, I would have to put in energy. As discussed, what's a really good place to find a surplus of energy in the cosmos in some small area? Core of a core collapse supernova, maybe? Yeah, especially that. So it turns out that to go from here to here in the core of a star, we're talking, this laborious process of billions of years, and then, more millions of years to get out to there. So this is like painstaking work at the core of a main sequence and giant or supergiant star. Everything from here to here was made during the fraction of a second of the subsequent months of decay of the core collapse supernova. This is how we know that we're actually a very recycled star system, is that it's not E equals mc squared where you're getting energy out to power your fusion by losing mass. In fact, you're making mass by taking energy, and that energy came from either the gravitational collapse or some other really energetic process, but all of this stuff comes from core collapse supernovas, and only during the core collapse itself, when there is abundant energy to be making things that weren't even elements. So all these exotic things are being made that don't even show up on the periodic table because they decay so quickly. So all that we see is the stuff that's relatively stable. And in the record of the elements that came from our solar system that we find here, there's all this exotic stuff like radioactive uranium and aluminum-26 is a weird one. You don't really find that too many other places, that tell us that this absolutely happened near us and that there was this wave of material that came off a core collapse supernova about 5 billion years ago or so. So all of this stuff, core collapse supernova bits. Right. So this is, you guys have heard this? Carl Sagan Just kind of panning dead center camera and saying, this is us, we're all star stuff or whatever. Okay. Other people prefer to say we're all nuclear waste, but
the cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself.
it's super enlightening. But again, we are nuclear waste. And that's absolutely true that all of that stuff came from the center of a core collapse supernova. So equivalently, for the low mass star life, there are a set of 6 or 7 stages for a high mass star's life. If you just get the whole supergiant thing, you're in good shape. So multiple shells, supergiant, all the stuff you can kind of condense into one. So cold cloud of gas, protostar, main sequence star, about 10 million years or so, maybe even less for a really high mass star. Supergiant. But then remember that almost unknowable and interesting things are happening on the supergiant branch. Could be burning anything from carbon core to silicon and inert iron shell. Supernova goes off after the core collapse. If the core collapse, if the neutrons are successful, you see a supernova for a month or two, and then the pulsar or neutron star will last for a very long time. So this is the kind of cartoony picture. Again, realize this is absolutely not to scale. So this is a huge cloud of gas, and this is something about like a small city or something like that. Very tiny ball of neutrons, incredibly dense. So freakishly not to scale, as always. So questions about that stuff? Okay. So I'll ruin everything by just pointing out that this is something that a physicist would kind of enjoy thinking about, is that, and we'll talk about what happens when gravity finally wins in a bit, is that you could actually think about the entire story of a star's life as the constant struggle against gravity. So in the cold star-forming cloud, basically PV equals nRT, thermal pressure, just molecular motion is fighting gravity. In the main sequence star, the radiation pressure from the light from fusion is fighting gravity. In a white dwarf, electron degeneracy pressure, what a normal person would call being solid, is fighting gravity. In a neutron star, the neutron degeneracy pressure, which is the greatest non-gravitational force that we can imagine, at least in strength. So neutron degeneracy pressure is very high, is fighting gravity. And in a black hole, finally gravity wins. So that's what we'll talk about in a bit. And we have the entire HR diagram covered. Right? So every single little bit. You still use it in the same way, but now you guys know where all of the bits come from. And then that's the usual set of questions. So this material will be on not the Friday quiz, but the quiz after that, next Friday. So any questions about that stuff?